Hey there, Chem Kids, Mr. C here, and today we're going to talk about sort of our first topic in our this chapter, thermodynamics. But before we really get into the nitty-gritty of everything, we need to understand the difference between heat and temperature. So temperature is physically a measure of kinetic energy. So it's how fast the molecules are moving, and not necessarily moving in space, but vibrating back and forth next to each other. So it's not like temperature is measured with kinetic energy of like me running across the room. It's more of the molecules themselves moving around each other is what creates it. And the more that they're moving or the faster that they're moving, the more temperature we are going to have. Heat, on the other hand, is the flow of energy. So temperature is a measure of the energy. It's something that we can use a thermometer to see. Heat, on the other thing, is something that we have to sort of calculate out. There are ways to measure it, but heat is the physical movement of energy from one object to another. So like we can move that temperature, and through moving the temperature and heat, or through moving that temperature and kinetic energy, that's how we get heat. So heat is the flow of energy, temperature is the measure of energy. Whenever we look at heat, the unit is going to be a joule. Whenever we look at temperature, we can do it in degree Fahrenheit, degree Celsius, or in chemistry, we'll see it a little bit this unit, more so in our gas unit, we can measure it in Kelvin as well. And then finally, heat is always going to flow from the warmer object to the colder object. So it always goes from hot to cold. It'll never go from cold to hot. Whenever things heat up or cool down, some things are better at heating up and cooling down than others. And the way that we quantify that in chemistry is by using something called specific heat. And it's basically how good something is at heating up. So the higher the specific heat, the more energy it takes to raise the temperature of that substance. And the lower the specific heat, the less energy it takes to raise the temperature of that substance. So one good example of this is the difference between sand and water. So water has a specific heat of 4.18 joules per gram degree Celsius. So it takes a lot of energy to heat water up. So that's why when you're at the beach, the water stays relatively cool. Whereas the sand has a very low specific heat. It's 0.66 joules per gram degree Celsius. And that's why the sand heats up very quickly. It doesn't take a lot of energy to raise the temperature, so it's going to heat up a whole lot faster than the water will. One way we can measure the specific heat of something is by using calorimetry. And the way that this sort of works is we have a sealed container that's filled with water, and we can place a hot sample of metal in that water. And by calculating out how much energy that block or that water gains, we can then see how much energy the metal lost as well. And using that information, we can determine what the specific heat is. So it's just one way of measuring the specific heat in the lab, which is how we do have to measure that specific heat. It's not really something that we can just calculate it out with numbers. We have to collect data first, and then we can collect it out, and that data is collected in the lab. We'll be doing this as well at the end of this unit, sort of on the last day. So how do we calculate out this change in heat? How do we figure out how much heat we're gaining or how much heat we're losing or transferring from object to object? Well, we're going to use this formula. Q is equal to mc times delta T. This is a fun formula. I like this formula. We're going to learn what all these variables mean. So the first one is Q. Q is the amount of heat given off or absorbed. Its unit is going to be a joule. So that's Q. That's the amount of heat given off or absorbed. So if it's being absorbed, we're going to say it's positive. If it's being given off or released, we're going to say it's negative. So like if we said we gave off this much heat or we lost the heat, that means it's going to be a negative Q. If we absorbed the heat, on the other hand, we're going to go ahead and say that that is a positive Q. Our next variable is M. That's going to be our mass. Its unit's going to be the gram. So anytime we have a problem where the unit on it is G, we know that that's talking about the mass. So it's just how much stuff we have. C is the specific heat, so that's not one of those weird units, the joule per gram degree Celsius. This is specific for each substance, and every substance has its own specific heat, even within the different states. So like liquid water has a different specific heat than ice, which has a different specific heat than water vapor. And then finally, we have this delta T. That delta, we're going to come back to that all unit. That's what this this triangle is there. But all that means is it's the change in temperature. And it's always going to be the final temperature minus the initial temperature, or what we ended with minus what we started with. And that's what the delta sign is always going to mean. So anytime you see that triangle, it's always going to be what we end with minus what we started with. So what does this look like in a problem? Say we have 5 grams of copper, which heated from 20 degrees Celsius to 80 degrees Celsius. How much was absorbed by the copper? The C is 0.38 joules per gram degree Celsius. Well, we know Q is equal to MC times delta T. So we have to identify what all these are. So we want to know how much heat was absorbed, which means we're looking at Q. So we need to figure out what M is, what C is, and what delta T is. M is always what has a G after it, so the M is 5 grams. C is the specific heat, which it tells us in our problem is 0.38 joules per gram degree Celsius. And then temperature, or the change in temperature, is that final minus the initial. Or in this case, we ended at 80 degrees. We started at 20 degrees, so it would be 80 minus 20. Or delta T turns out to be 60 degrees Celsius. We have all of these numbers now, so all we got to do is plug in. So we're going to say Q is equal to our mass, which is 5, times our C, which is 0.38, multiplied by the change in temperature, which is 60. When we plug that all into our calculators, which hopefully you're doing this if you're watching it at home, we would find that we would be releasing, or absorbing in this case, 114 joules of energy there. Another type of problem that we might see is maybe instead of calculating the heat, we're actually want to calculate specific heat. So like in this case, we want to calculate the specific heat. So in our Q equals MC delta T, we're actually looking for C. So we have to identify out what Q is, what M is, and what delta T is there. And because I know normally we write this as Q is equal to MC delta T, but because the order of multiplication doesn't matter, we actually pulled C out to the front. And usually it makes it a little bit easier if whatever you're solving for is in front, but you could leave it in this form if you wanted to as well. Our Q value is always going to be the number that has a joule after it. So because this has a J, our Q is going to be 10 joules. Our mass has a G, so that's going to be 3.1 grams. And our change in temperature, well, in this case, we don't have to do that subtraction thing, but because it tells us that it rose by 17.9 degrees Celsius, so the change in temperature is however much it rose by, which is 17.9. Next, I'm going to start plugging into this formula. So my Q is 10, which is equal to C times the mass, which is 3.1, times the change in temperature, which is 17.9. I'm going to do 3.1 times 17.9 first, and I get 10 is equal to 55.49 times C. To get rid of that 55.49, I'm going to divide by it on both sides, because that's how I get rid of it. 5.49. So it sort of cancels out over here, and I'm left with C is equal to 10 divided by 55.49, which gives me a nice value of 0.18 joules per gram degree Celsius. And that is what my C would be. I don't know why it says no there. I'm going to cross that out. So that would be the problem for that. That is all that I have for you in these notes. I look forward to seeing you in class. Try to work on problems. I believe it is... Oh, come on, Mr. C. It is 1 through 5 in the packet. 1 through 5 in the packet. The answer should be back there and ready to go.